Hello everyone. So today we are going to learn about best average and worst case, and then we'll talk about asymptotic notations. Alright, so let's start with the video. So first of all, let's talk about best average and worst case. Alright. So first of all, let's take this example. This is the same example which we took in our previous video. So it is in this we have to find sum of first and natural numbers, and for this we use a loop which runs from 1 till n, and when we add all the iterators and return the sum. All right. So as we told before, what would be the time taken here? It will be c1 n plus c2. All right. Now c1 n because we are operating this expression n times, and C2 for declaring declarations such as sum is equal to 0, I is equal to 1, etc. etc. Alright. And then what will be the order of growth? To find order of growth, what we'll do, we'll ignore all the lower order terms, so C2 gets ignored. Then we'll ignore the leading coefficient of leading term, which is what, C1. So we'll ignore C1. We are left with n. So order of growth here becomes n. Alright. Now let's take another example. Yeah, um, So in this, we are doing the same thing. We have to, find sum of n natural numbers, all right? But if n is an even number, like we have a condition here, if n%2 is equal to 0, which means if n is an even number, then we don't have to find sum, then we just have to return 0, all right? So in such cases, we cannot make a general statement regarding order of growth. All right, because see, if n is even, then we'll just simply return 0. So order of growth would be what? Constant. But if n is an odd number, then we have to go through this loop, and then the order of growth would be n linear time. All right. So in such cases, what we do, we divide all the cases into three cases, into three parts. So one is best case, average case, and worst case. All right. So let's first talk about best case. So best case is the scenario where we have the least order of growth, meaning which takes the least time. So in this example, if n is an even number, suppose it is 4, 6, or 8, then we'll check if n is even, which it is, then we'll return 0. So this will take what? Constant time. Hence the best case here would be a constant, right? Now let's talk about the worst case. Worst case would be in the scenario which has the highest order of growth, which takes the most time. So in here, suppose n is odd, like 3, 5, 7, 9, or something. So we have to go through this loop. It will take, linear time. All right. So hence the worst case is a linear time. All right. Now let's talk about average case. All right. So in average case, we assume the frequency of all the cases, and then we divide the total number of and divide the result by the total number of outcomes. Okay. So let me tell you what I mean through this example only. Suppose I am assuming that even and odd number both are equally likely. All right. Hence, suppose in best case, because there are only two cases, only it can be even. The number can either be even or it can be odd. So in the best case, it is even. So what will be the time then? C1. Then we'll go what if n is an odd, it would be the worst case, which would be what? C2 n plus C3. then what did I tell you? We'll divide it by the total number of outcomes. There are only two outcomes, even or odd, so we'll divide it. Alright, so what would it result to? Right, that is our question. So suppose C1 plus C3 by 2, we take it as another constant, C4, and we take C2 by 2 as another constant, C5, C5, right? Hence, what would be the order of growth? N, hence linear. So this is how we compute best case, average case, and worst case. So you learned about all these things. But now let's talk about which would be better in practical use. Alright, first let's talk about worst case. First let's talk about average case. Okay, so direct, if I tell you, we cannot use average case at all. Alright, the simple reason is we have to make assumptions on our own. And different programmers may assume different distributions, and it may lead to like different average cases for different people. Alright, suppose I took occurrences of even and odd as equally likely. But suppose some another programmer takes it like 90% frequency would be of even and 10% frequency would be of odd, then his average case would be different than mine. So average case is not efficient for different programmers. All right. Now let's talk about best case. So again, simple direct answer. We cannot use best case also. Okay, let me give you an example. Suppose you made a software, all right, and you want to sell it to some company, and you tell them that the best case for this is 0.01 millisecond or something, all right. But then you tell them that this is the best case, and I don't know like what would be the worst case. It can be even hours, it can be days, anything. So by common sense, you can say that you would be pretty sure that no one will buy your company, buy your software, all right. So that is it. So the only case which we are left is worst case. All right. So this is what we use most of the time because it tells us the max time our program is going to take to execute. And this would tell us the exact efficiency of our program. Okay. So this was all about the best, average and worst case. Now let's go to asymptotic notations. All right. So as we talked previously, asymptotic notations are used to define asymptotic analysis. All right. So let me tell you about what are asymptotic notations. So asymptotic notations are mathematical notations which represent the growth of any mathematical function. All right. There are three famous notations which we'll talk here, which is big O, which tells us about the exact or upper bound on order of growth. Then there's theta, which tells us the exact order of growth. And then there is omega, which tells us exact or lower bound on order of growth. All right. So you'll understand better if I tell you through an example. Suppose this is an example. It is a program to find target element in an array. All right. It is a basic linear search program where we take arguments as in an array, size of it, and the number which we have to find. So what we'll do, we'll run a loop for I0 till I less than n. And if we find the target element in the array, we'll return the index where we found it. Or if we did not find it, we'll just simply return -1. All right. So this is like the case when which we saw in best, average, and worst case. So this is like quite somewhat example like that. Suppose if my x here is 10. All right. Then what would be my order of growth? Constant. Was it the first term? I'll just go into the loop, I'll find and I'll return. So it is, constant term. But what if my x is, somewhat 75? Then I'll iterate through whole of the loop. I'll come out of it and then I'll return -1. So what work did I do here? Linear work. All right. I, you know, run through the loop n times. So I did a linear work. So here also there are two cases: best case, worst case, or average case. Okay, average case can be like any intermediate number, 30, 40, or something. All right, so you can guess it. All right, let me talk about best and worst case here. All right, so best case is linear. Best case is constant time, and the worst case is linear time. All right, so then there would be like multiple lines. Key my best case is constant, and then my worst case is linear time. But instead of this, I can simply write that the time complexity of this operation, it is big O of n, right? Now might be wondering why. See here, big O is what? It is exact or upper bound on order of growth. So the time complexity here can be what? It can be either linear or it can be either constant. So big O of something like big O of order of growth, which is n here, which is linear, it tells us that either the time complexity of this function is linear or less than that. So what is less than a linear? It can be constant. Hence big O tells us that big O of order of growth tells us that it is either exactly equal to that or it is less than that. Now let's ON here. Cool. I hope you understand that. And now let's talk about theta. So theta is, represented like this. Suppose I wrote theta n. So this means that it is an exact order of growth. All right. So for this search operation, you cannot write theta of n because it means that this program will take linear time. But what if the target element is 10? Then we will have only constant time. Hence, we cannot use theta n here because it tells us the exact time. All right. Now let's talk about omega. What you can write here is omega of 1. Okay, 1 here means constant time. Right. So omega is, exactly opposite of big O. So omega of any order of growth means it is either equal to that or it is higher than that. Means it can be either a linear time, it can be either a constant time or it can be higher than that. That means either linear, quadratic, or anything. So for this function, we can write omega of 1. So this means that it can be either of constant time or it can be greater than that, which can be like linear or anything. Now you must have guessed that we cannot use omega function mostly because you know what, it tells us the best scenario and it does not take account of worst case. All right, as I told you in the average in the previous section, that if you made a software and you tell the best case but you don't know about the worst case, then you cannot use it. So that is what omega does. So what we use basically here is only big O and theta. which I told you about. To make things more clear, let me tell you about this. Yeah, let's take this example. We have used this many times. It is the same one where we have to find the sum of first and natural numbers. All right. So can you like pause the video and guess the time complexity of this one? All right. So it is can be either theta. All right, my bad. Yeah, it can be either theta of n or big O of n. All right. I must be wondering if you have got it very well, but let me still tell you like why. See this loop. No matter what, this loop will run n number of time because there's no condition inside it that it has to stop or anything. Like it was there in the upper example. So this loop will run for n number of times. Hence, we can find the exact time complexity of it, which is theta n. I must be wondering why I said big O of n. So let's go up and see why. Because see, big O tells us exact or upper bound. Big O tells us the exact or upper bound. So we can say like big O of n also here. Alright. Yeah. See, many a times we only have to tell either theta or O. Big O. Are you getting my point? See, in many times you've been asked question like what would be the time complexity of this, and you cannot tell both of them. So the one which you'll tell should be the most efficient one. Okay, so big O of n is what? Key it is either of linear time or less than that, which means constant. But you can clearly see here that no matter what, it will take n loops to run it. Hence, the time complexity would be, the time taken would be linear. Hence, theta n would, work here. I'm not saying big O of n is wrong, but sometimes the question comes like, we have to tell either one, only one. Either it can be theta of n or big O of n. In such cases, we'll use theta of n. Alright. So I hope you get the asymptotic notations. Among these, big O and theta are the important ones. Omega is not used as much and you'll really see it in your future. So concentrate on big O and theta. And I'll end this video today. And in the next video, we'll take some examples and we'll see the time complexities of the programs, and then you'll understand more about when it would be a big O or when it would be theta. And there would be examples when we'll take omega, so don't worry about that. All right. So on this note, I'll end this lecture.